So far we discussed about how to design helical gear also. So in that we have seen how we can convert an helical gear into an equivalent virtual spur gear. Then we design the helical gear like spur gear. Once we converted the parameters of helical gear into equivalent parameters of a spur gear, so we adapted the same procedure for the helical gears also and we designed it. So next we'll move on to the another category of helical gears. So which we'll call them as herringbone gears. So here you can see in the picture here, if you have both ends of helix on a single gear like this, left hand as well as right hand. So this is right hand, this is left hand. So this kind of gear we call it as herringbone gear. And the other one here you can see that here you can see there are two gears. So but in each gear there is only one kind of or one end of helix, either left hand or right hand. So in this left hand, in this it is right hand. So there is only a helix. Whereas in this gears here, this is the meshing point. So each gear have both ends, left hand as well as right hand helix, both the gears. So this type of helical gear we call it as herringbone helical gear. And this one you have, since you have two helical gears with the two different ends, we'll call this one as a double helix angle. So why we are discussing about this herringbone or double helical gears? While discussing about the force analysis of a helical gear, in case of helical gear, the force there are three components of forces, that is PT, PR, as well as you have a axial load or a thrust load. So in case of spur gear, you have only PT and PR. You don't have any axial load. So this axial load, what happens? We'll call it as thrust load also. We'll call this one as THRUST, thrust load. And this thrust load will create a large reactions on the bearings. So therefore, so if you want to avoid this thrust load, still if you want to use helical gear, then you can go for either herringbone gears or double helical gears. Either you can choose herringbone gears or double helical gear. Other than that, the design procedure, everything is similar to your helical gears only. But here, the advantage of this herringbone gears or double helical gears is they eliminate the axial force. See, this axial force is arising due to this helix angle. So, like I said, in case of a spur gear, you don't have any axial force. So, because your spur gear teeth are cut parallel to the axis. So, because of this, you have only radial and tangential component of forces. So, since the teeth are parallel to the axis. So, on the bearing here, whatever bearing you have here or maybe somewhere else, in the bearing here, they are not going to produce any axial reaction in this direction. So now, if I take a helical gear which is having a something like a single helix, single hand, so that is either left hand and then right hand, something like this, because of this helix angle, it will produce axial reactions or axial forces on the
Hello. 48. Are you able to hear me? 48 or 54?
Yes, sir. Yes, sir.
From my side here, power failure is there. So my laptop was disconnected. I'll try to connect again once power come back. So be on the class. As and when power comes now, I'll join the class. So right now
Okay,
I
sir.
can't. I'm talking through my mobile. So I'll disconnect this. So when a power comes, you just be in the class. When I power came back, I'll reconnect to the class. Okay. So
Okay, right. So the purpose of this double helical gears or herringbone gears is to eliminate the axial thrust on the bearings. So that's what we are going to discuss. Apart from that, the design procedure, everything is same, similar to the helical gears only. When a pair of helical gears transmit power, both input and output shafts are subjected to a thrust load. So this is the drawback of helical gears. Even though they are capable of transmitting more power, but they will transmit the thrust loads. So the shafts are subjected to the thrust loads. So these thrust forces impose reactions on the bearings. This will increase the size and cost of the bearings because the bearings has to withstand higher forces. So therefore, obviously the size should be more. Or if the size increases, the cost of the bearings also increases. The thrust forces on input and output shafts can be eliminated by using herringbone or double helical gears, which we already discussed. Both types of gears are constructed by joining two identical helical gears of same module. So this is the condition here. The module should be same on these two gears. Here these two are joined. Here also two gears are joined, but here hand to hand it is joined. Here there is a clearance. That is the only difference. Number of teeth and pitch circle diameter. See, for both the gears, the module should be same, the number of teeth should be same, and also the pitch circle diameter should be same. You can see that the diameter is same for both the gears. Here also you can see both diameter is same. Then diameter, pitch circle diameter. Obviously, if module is same, pitch circle diameter is same, the number of teeth also would be same. But with the teeth having opposite ends of helix. Hello? కనెక్ట్ అయిందా? అది గ్రీన్ కలర్ వచ్చిందా లేదా? ఒకసారి ఆ ఇంటర్నెట్ మీద క్లిక్ చేసి చూడు వస్తుంది. ఏంటో రావట్లేదు. ల్యాప్టాప్లోనా ఫోన్లోనా? వైఫై కనెక్షన్ దగ్గరికి వెళ్ళి కనెక్ట్ చేయి. కార్తికేయ అని పేరు ఉంటుంది దానిలో కోసం. దాంట్లోనే నెట్లోనే ల్యాప్టాప్లో. ఓకే, సో they should have same module, same number of teeth as well as pitch circle diameter, but the end of helix should be opposite. You can see that here each gear, say this one, here it is opposite. For each gear it is opposite. End of helix should be opposite. So here also you can see that. So by this you can construct the either herringbone gears or this double helical gears. The basic difference between herringbone and double helical gear is there is a groove between the two helical gears in case of double helical gear, while gear without a groove is called herringbone gear. So that's what I already said. So in case of this one, we are calling it as a double helical gear. So in this you have a groove here. So whereas in case of herringbone there is no such groove. This type of groove is not there. They are joined hand to hand here. So therefore, this we'll call it as a herringbone gear, and this one we'll call it as a double helical gear. That is the only basic difference. So other than that, everything is same. Double helical gears are cut on a single gear blank. So these two gears are cut on a single gear blank by a half with a tool run out groove between the ends of helix. So with a tool run out between the, to form this groove, they will use a half tool. Herringbone grade is cut by the two cutters, which reciprocate 180 degrees out of phase to avoid the clashing. So these are the how we are going to fabricate this herringbone and double helical gears. So this is the process. So herringbone and double helical gears offer the following advantages. So the advantage is nothing but only thing is you can avoid or you can eliminate the axial thrust force. That is the advantage of this double helical gear. Because you are constructing the two gears, then thrust is going to increase. That is going to be the disadvantage. So the advantage is they develop opposite thrust reactions and thus cancel out the thrust force within the gear itself. The net axial force that acts on the bearings is zero. That's what we already said. So if you use the purpose of constructing these herringbone gears or double helical gears is to cancel out that axial force or thrust force. So that is going to be the one advantage. The power transmitting capacity is high because you have two gears. With one gear you can produce, if you produce 10 kilowatts power, then since in a helical gear or double helical gear, you can produce twice the power because you have two gears are there. So therefore the power transmitting capacity will be high. High pitch line velocities can be attained with herringbone and double helical gear. So you can go for high pitch line velocities V. So that is nothing but pi d n by 60. So then you can go for high speed applications also. If you can run these herringbone gears for large speeds, so then you can have a large pitch line velocities also. Okay. So those are the advantages. Then coming to the disadvantages, herringbone and double helical gears are very expensive compared to the helical gears. Like I said, because you are constructing the double gears here, obviously the cost is going to increase. So therefore, these are expensive when compared to the spur gears. Both herringbone or double helical gears, they are expensive. Then the other disadvantage is balancing of thrust force depends upon the equal positions of load between the right hand and left part of the gear. So here we said the advantage of this herringbone gears is they can cancel out the thrust in the gears itself. So that means if one gear produces the thrust force in the rightward direction, the other force is generate the thrust force in the leftward direction. So then we are saying that these two forces will cancel out each other. Therefore, net thrust force is going to be 0. So when this is going to be happen, if you mount those gears precisely, so that means if both gears are producing same amount of thrust force, of course in magnitude, directly is going to be opposite. In magnitude, if both gears are producing the same amount of thrust force, then only it is possible. So that means the balancing of thrust force depends upon the equal distribution of load between the right hand and left part of the gear. Therefore, a high degree of precision is required to locate herringbone or double helical gears axially on the shaft. So that's why you required a large precision here. While cutting the gears, you should have a better accuracy, or you require more accurate cutting of the gears on the blank. So this will going to be costly again. So if any deviation from that, obviously the axial force is not going to be cancel out each other. So if the location of that forces gear is not exactly matches with the opposite one, then there is a resultant thrust force will be there. It is not going to be 0. So therefore, you require high degree of precision in case of this herringbone gears. Okay, that's what is it. Therefore, a high degree of precision is required to locate herringbone and double helical gears axially on the shaft. They must be aligned accurately. If each half is to take exactly one half of the load, so you need to align them accurately. One method of alignment is use the thrust bearing for one shaft only and allow the other shaft to float axially. In this case, the gear tooth forces automatically position on the other gear so that no external forces are present. So that is one alternative for that. So anyway, so the disadvantage here is it requires high degree of precision while mounting the gears on the shaft. That is the thing. Herringbone and double helical gears are used in high power applications. So we already seen that as an advantage. This one is the advantage. That is, you can transmit large amount of power or torque through this herringbone or double helical gears. So the examples for that is ship drives and turbines. So you can use this herringbone gears in case of ship drives and turbines. The helix angle for a single helical gear is from 15 degrees to 25 degrees, whereas for herringbone and double helical gears permit higher helix angle because there is no thrust force. So there is a limitation for helix angle in case of a single helical gears. Always you need to choose the helix angle between 15 degrees to 25 degrees. Why? Because this will limit the thrust force. If it is goes on increasing, we know. So sin alpha. So sin alpha is, if alpha increases, sin value will increase. Even tan value also increases. If you look at the expression for the axial thrust load, PA, it is a function of your helix angle. If helix angle increases, your thrust force will also increase. So that's why always it should be kept less than 25 degrees. Whereas in case of this herringbone or double helical gear, there is no issue of thrust force, then you can go for higher helix angles also. The helix angle for herringbone and double helical gears is ranging from 20 degrees to 45 degrees. You can go for up to 45 degrees. The design procedure and design equations for herringbone and double helical gears are the same as for single helical gears. So whatever procedure we adapted for the single helical gears, we can use the same procedure for these double helical gears also, or herringbone gears also. So, but only thing what you have to do is, what is the consideration you have to consider here in design? Herringbone or double gear is considered as equal to two identical helical gears, each transmitting 1/2 power. So that means, so earlier we had taken power is equal to 10 kilowatts. Power to be transmitted is 10 kilowatts means, so for while deriving the while designing the gear, we are taking it as same because you have only one pair of the gears. So we are designing for one gear, you have to take PA. But now onwards, if it is a herringbone or a double helical gear, you have to take only half of this power, that is 10 divided by 2. So only you have to design the gear for 5 kilowatts because you have a two gears here, either in a herringbone or double helical gear. There are two helical gears, so you need to reduce the power to the half, and based on that half of the power, you need to design the helical gears. Okay, so this is about this herringbone and helical gears. Nothing that much great or important. So only thing is the difference is here these are used to eliminate the axial thrust forces in the shafts or shaft bearings. So that is the condition why we are going for the herringbone gears. So in case of the herringbone gears, since you have two gears, you have to design these gears similar to the single helical gears, but only thing is you have to consider only the half of the transmitted power to design the gear. You need to consider only half of the transmitted power for designing the single gear. Okay. So anyway, this next numerical example will illustrate that. You note down this example and then we'll discuss with this. We can close this topic also. So I think with this we have all the topics are covered. I think our syllabus is entire syllabus is covered. Okay, just note down this problem, take a 2 minutes time and note it down. Then we'll discuss the solution and we'll close it. Of course, the solution is similar to your helical gear only. Here, only thing what you need to do is in this. He has given the power 100 kilowatts, but you need to design it for the single gear for 50 kilowatts. That is the only difference. Anyway, note it down. So then we'll discuss the solution. హలో కనెక్ట్ అయిందా? ఏం చేస్తున్నావు నువ్వు? Are you able to hear me?
Yes, sir.
Is it completed? Did you note down it or not?
Yes, sir.
రెస్పాండ్ అవ్వాలి. ఆ నోట్ చేశారంటే చెప్పరు మెలగొంటారు 100 సార్లు అడగాలి అది కూడా.
సార్ నోట్ చేశాను సార్.
నోట్ చేశాను సార్.
ఇప్పుడు ఏం చేశారు? Okay, right. So here, like I said, so the design is should be based on 50 kilowatts. Other than that, it is similar to the single helical gear only. So first I'll read out the data in the problem, then we'll discuss the solution. So here, a herringbone speed reducer consists of 24 teeth on pinion and 104 teeth on gear. So there is number of teeth on pinion and number of teeth on gear is given. Normal module value is also given 2 mm. Pressure angle is 20 degrees given. Helix angle is 25 degrees. Pinion receives 100 kilowatts power through its shaft and rotates at 3600 rpm. So pinion speed is also given. Power transmit to be transmitted is 100 kilowatts. The phase width of each half is 35. See, you can see here only half of the value has given phase width. So 35 mm. So because we need to design for half of the power. Here you have to consider, since it is a herringbone gear, you have to consider the half of the phase width. The gear is made of alloy steel with SUT 1500 Newton per mm square. Then surface hardness is 450 BHL. Service factor is 1.25. Determine the factor of safety against the bending failure and fitting failure. So that means, so you need to calculate what is the factor of safety against bending failure and against fitting failure. So that means you have to calculate what is the beam strength and what is the wear strength. If you know beam strength and wear strength divided by the P effective is going to be the factor of safety against the bending failure, and wear load or wear strength divided by effective load is nothing but the factor of safety against fitting failure. So straightforward and simple only. So now I'll show you the solution for this. So this is the given data. Power is 100 kilowatts. Speed of the pinion 360 rpm. Number of teeth on pinion 26, on gear 104. Helix angle 25 degrees. Normal module 2 mm. Pressure angle is 20 degrees. Of course, it is normal pressure angle. Phase width B is 35 mm. SUT 1500 Newton per mm square. Service factor 1.25 and BHN is 450. Since herringbone gear consists of two identical pairs of helical gears, the power transmitted by each gear is, you have to take the, like we discussed, we have to take half of that power, that is 100 divided here in the problem given 100. So we need to divide that one by 2. So therefore, each pair, each gear has to transmit only 50 kilowatts. So now we have to take 50 kilowatts power, and based on that you need to design. So for that, first we'll find out what is the tangential force. This is the formula for the tangential force. So in the power, you have to consider only 50 kilowatts. So everything is given. Speed of the pinion is given as 3600. Then you will get this as your torque transmitted from the power transmitted. So once you have torque transmitted, from this you can calculate the tangential load provided if you know the pitch circle diameter. So for that, first we will calculate the pitch circle diameter of the pinion. So for that, the formula is this one, ZP, number of teeth on pinion multiplied by normal module Mn divided by cos psi. Everything is given in this. Just I'll substitute the data. I'll get the pitch circle diameter of this virtual spur gear. This is the pitch circle diameter of the virtual spur gear, which is 57.38. So now, using this dp dash and mt, you can calculate pt. So pt is nothing but 2mt by dp dash. So if you substitute mt and dp dash value, you get the tangential component of the force as 4622.83 newtons. Then you can calculate the, from this pt, you can calculate the effective load. Effective load is nothing but your cs into pt plus pd, or if you want to go for Buckingham equation, you have to use pd. Or if you want to use velocity approach, velocity factor approach, CS into PD plus or CS into CV into PD. That is going to be the effective load. So for that, to compute CV, that is velocity factor, you require V. V is nothing but pi dp dash Here dp dash np divided by 60 into 10 power 3. So I know everything in this. I can calculate the pitch line velocity v, which is nothing but 10.82 meter per second. If you substitute the respective data and you calculate that, you get it as 10.82 meter per second. Then the formula for CV is fixed. Irrespective of velocity here, this is going to be the CV formula. So of course you required a V here in this. So 5.6 plus flow rate V by 5.6. If I substitute that one, I get 1.5874. So once I know CV, then I can calculate P effective. P effective is nothing but CS into CV into PT. That is CS is 1.25 given. CV just now computed as 1.5874. And this PT is already calculated as 4,622.83. If you substitute this, you'll get the effective load as 9172.78 newtons. So 9172.78 newtons is the effective load. So now I know the effective load. Then if I calculate SB, that is beam strength, and SW, then I can calculate the factor of safety against bending failure. That is nothing but SP divided by your P effective is going to be the factor of safety, or SW divided by P effective. So that is nothing but the factor of safety against the fitting failure. So he asked us calculate these two. So therefore, what you require is now you need to compute what is beam strength, what is wear strength also. So for that we know the formulas. Beam strength as well as wear strength, we know the formulas. First we will consider the beam strength. So for that, in the formula for beam strength, we have a Lewis form factor. Capital Y is there. That capital Y is calculated based on the virtual number of teeth. So for that, first you need to compute what are the virtual number of teeth on the pinion. So the formula for that is Zp divided by cos cube psi. So Zp is given as 26, psi as 25 degrees. Therefore, the virtual number of teeth is going to be 34.93. So now for this 34.93 teeth, you need to calculate what is the Y. Using data book, you need to use the interpolation formula. So for you have a form factor Y value in the table 28.33 for 33 number of teeth as well as 35 number of teeth. So using these two values, you can interpolate so that you will get the Y value for 34.93. So Lewis form factor for 34.93 teeth is obtained by interpolation, not interpolated, from the table 28.33 of your design data handbook. So for 33 teeth it is 0.367 and for 35 teeth it is 0.373. If you refer the table 28.33, so in that you can clearly see that for a pressure angle of 20 degrees, if the number of teeth are 33, your Y is 0.367. If number of teeth is 35, Y is going to be 0.373. So then using those two values I can interpolate and I will get the Y value. So once you got Y value, then you know the normal module, you know the B value. So your sigma B is nothing but SUT by 3. So that is also given, SUT is given. So you can calculate sigma B, which is nothing but SUT by 3, which comes out as 500 Newton per mm square. So now you know everything. So in the formula for beam strength or bending strength. So that is Mn into B into sigma B into Y. Just you need to substitute this data into this and you need to evaluate what is the beam strength. So that is nothing but Mn given as 2 mm, B is 35 mm, sigma B is 500 computed now, and Y also evaluated as 0.37279. So if you substitute and simplify this, you will get the beam strength as 13,047.65 newtons. So once I know the beam strength, I can calculate the factor of safety. That is nothing but beam strength divided by the effective load. So similarly, in order to calculate the factor of safety against the fitting failure, you should know what is the wear strength also. So we know the formula for the wear strength. In that formula, you require Q, that is ratio factor. So which is nothing but 2 into Zg divided by Zg plus Zp. He has already given the number of teeth on gear as well as pinion. You can easily calculate the Q. If you substitute the data, you will get Q as 1.6. Then this is the formula for sigma E, because you need to calculate K also. In your beam strength formula, you have a K is there. So for that, you require E sigma E. So sigma E formula is like this: 2.8 times BHN minus 70. He has given the BHN value. So BHN is given as 450. If I substitute it, I'll get it as 1190 Newton per mm square. So then, using the sigma e value, I can calculate the k now. K is sigma e square sin square alpha n into 1 by e1 plus 1 by e2 divided by 1.4. So this is there in the data book. I am not taken from anywhere else. So whatever material I share it to you, in that it is there. I have taken that. So I am not following the textbook formula. If you want to follow the textbook formula, it is going to be 0.16 into BHN by 100 whole square. So, but in the examination, you will provide with the data book. So I am using the same formulas which are there in the data book. So using those formulas only, we will try to solve this. So now we got sigma E as 1190. So if you substitute that, and alpha n as 20 degrees and E1 as 2000, 2 into 2.07 into 10 power 5. If you calculate that, you'll get K as 3.3425. So once you have K value, then you can calculate wear strength. SW is nothing but, here it is dp dash, BQ dp dash K divided by cos square psi. This is the formula. B is given 35, Q calculated as 1.6, dp dash is also calculated as 57.38, and K is computed as 3.3425 here. So then cos square 25 degrees. So then from that you'll get your wave strength as 13,075.98. So once you have beam strength as well as wave strength, then you substitute, you can calculate the factor of safety, because we already know the effective force also. We already calculated P effective also. So factor of safety against bending failure is SB divided by P effective. So SB is 13,047.65 divided by the effective force is 9172.78. So you get it as 1.422. So the factor of safety against bending failure is 1.42. Similarly, you can calculate the factor of safety against the fitting failure, which is nothing but SW divided by P effective. SW is 13,075.98 divided by effective force is 9172.78 newtons. So then if you compute the ratio, it comes out as 1.425. So for both the cases, you get around 1.4 or 1.5 as the factor of safety. Right? So this is how you can solve the problem. Right? See, if you observe the solution, it is not going to be a different one. It is quite similar to your helical gear problem only. So how you are designing single helical gear, the same thing here also. Of course, here it is not a design problem. Just you just calculate what is the factor of safety, but the approach remains same. Only thing what you need to consider is, so in the from the total power while designing the gear or while calculating the parameters of the Okay, so again, power failure. A lot of interruption is there today. 3 times it was connected and disconnected, so like that. Anyway, so this is what I want to discuss. I think we already discussed the solution also for this. With this, I think we can close this topic also. Okay, right. So already discussed the solution also. We have to consider only 50% of the power, which is 50 kilowatts. Then based on the 50 kilowatts, you need to calculate what is the PT value. Then to this PT, you need to apply what is the service factor and what is the velocity factor, so that you will get the Phi effective. So that is the first step. Calculation of the Phi effective is one step. So then calculation of the beam strength and weight strength is the second step. After that, in third step, you can calculate the factor of safety. Okay, right. If you have any doubt in this, you can ask your doubts. So not only in this, anything. So anything you have any doubt, you can ask it now. So from the next class onwards, what we will do is we will try to solve the previous examination question papers one by one. First we'll take up gear problems, then we'll move to the next like that we'll take up. So today, if you have any doubt, you can ask it now. So I think I'm done with my discussion or presentation. If you have any doubt or anything else, you can ask it now. If you want to note it down, you can note it down also. Or else, if you know the procedure, you can solve on your own also, no issue. Okay. Or else, if you already done it, just respond to the attendance sheet. I think I already placed the attendance sheet in the class now. Note, respond to that, and you can leave the class.
సార్ ఒకసారి లాస్ట్ స్లైడ్ పెట్టండి సార్.
నెక్స్ట్ వన్
దీని తర్వాత సార్.
దీని తర్వాత వేర్ స్ట్రెంత్ తర్వాత వేర్ స్ట్రెంత్. ఓకే,
ఇదే సార్.
ఓకే, నో డౌట్. మస్తాన్ అయిపోయిందిరా